In this module, we want to discuss unsupervised learning. One specific methodology we want to discuss is clustering. Here are the key topics that we want to discuss. One of them is k-means clustering algorithm. If you ever heard of k-means, that's great. It's an opportunity for you to learn what is k-means and what is clustering. And after that, we want to discuss k-means application and other methods, followed by Gaussian mixtures. Key topics in this module. Clustering is trying to do group similar instances together into different clusters. For example, you could use it for some data analysis. You could use for customer segmentation. So if you ever heard of customer segmentation, it's a good opportunity for you to learn here. If you never heard of customer segmentation, the idea is trying to segment the clients or customers in many different scenarios, such as in a marketing campaign. You want to know what type of customers that you may have, and then you use different marketing strategies. Recommendation systems, different segmentation of different products so that you can recommend different items. Search engine, image segmentation, and in semi-supervised learning, and in dimension reduction methods, and more, so that you could leverage clustering algorithms. Another topic that we kind of touched upon in this module would be something called anomaly detection. So idea is to learn what normal data looks like and then use that to detect abnormal instances. We also mentioned in this module that not only anomaly detection, the other thing is called innovative detection. So to see maybe some new points that's different from previous data points. But by all of this, right, is the key idea is still to learn what normal data looks like first. Third topic we want to touch upon would be density estimation. Estimating the probability density function of the random process generated the dataset. And then this can help with anomaly detection and can also help with data analysis and data visualization. So first of all, let's look at what is clustering. So if you recall the iris data is a bunch of flowers, right? In that data set, it has three types of flowers: setosa, versicolor, and virginica. And it comes with 4 dimensions. One dimension is sepal length, second dimension is sepal width, and then third dimension is petal length and petal width, right? So for those 4 dimensions, it comes with a class of the flower. And the class turns out to be those 3 different types of flowers. So if you recall, we leveraged multiple methodologies to study iris data for the classification methods, including logistic regression. We studied support vector machines on iris data as well. We even studied feature importance. Remember, we said, okay, those 4 dimensions, 2 of them turns out to be more important. And also we studied decision tree and random forest on iris data as well. So now you get a sense that we're trying to learn all kinds of machine learning algorithms, and at the end, we need to somehow put them together. But now let's just continue to think through, right? Other than clustering, other than classification, what if we do not know the label of the data? In other words, we don't know which flower types of data belongs to. so that we don't have a label of the data. Now it becomes unsupervised learning. Now, what you saw would be on the right-hand side. For us, it's just a bunch of data points, and x-axis is petal length, y-axis is petal width, and then we are hoping that if we run some sort of algorithm that we don't know which class this belongs to, we hope that with that algorithm, it can help us to decide which class each one of them belong to. So conceptually, you probably would be thinking this belongs to one class. Maybe this would be belongs to the other one. Ideally, if we can differentiate this class with the other one, then that would be ideal, right? This methodology is called clustering. So let's continue with a different data set. So this data set is coming from 5 blobs of instances that's initially designed by, in 1957, Bell Labs by Lord and Forgy, and then they designed some algorithm called kmeans. And then this data set have different blobs. And then hopefully, right, you have a x1, x2, hopefully you would be able to cluster all these data set into 5 different classes. 1, 2, 3, 4, 5. So let's say if kmeans can help you with that. What you do is you import kmeans class and then set a number of clusters into 5. And then you can initiate, you have this initialization of k-means, and then you could use one of the method called fit_predict to predict the clusters of each one of them. So let's look at the y predict. It turns out to be, right, for each instances, it has corresponding clusters, 0, 1, etc. The first point belongs to fourth cluster in the data. And then actually let's look at the cluster centers. This is more meaningful. So cluster centers, the first cluster, the center is negative 2.8, 1.8. So where is it? Negative 2.8 somewhere here and 1.8. So right here, right? So this one is the first cluster. Of course, in terms of index, it's cluster 0, right? So that's cluster 0. And the second one is 0.2 and 2.25 here, right? That's the second cluster, index would be 1. Third cluster, negative 2.79, somewhere here as well, and then 2.8. So it would be here, right? So remember, this is 1, 2, 3. How about 4? 4 is right here. Fifth is right here. So 1, 2, 3, 4, and 5. So those are the 4 clusters, and each one has something called cluster center, the centroid of all the data points in that cluster. So let's see how this algorithm works. Before we actually get into the algorithm, first thing that let's say if you have, this is output of the k-means clustering. So say that this is first cluster, second one, we said third, fourth, and fifth, right? So now we can assign new instances. And then the new instances would be 4 data points. One of them is 0, 2. For example, 0, 2 would be somewhere here. We hope that it would be assigned to the first cluster, which is index 0. Right? So now we oh, 0, 2 is right here. So index is 1, right? So that's 0, 2 right here. So let's look at these all the data points, right? So those 4 data points, 0, 2 is the first one assigned to index 1, which is this cluster. We said this is 0, this is 1, this is 2, 3, 4, right? So this 0, 2 goes to that. That's great. You use predict on the xnew to know which cluster it belongs to. How about 3, 2? 3, 2 is all the way there, somewhere here. So with the hope it would still be this cluster. How about negative 3 and positive 3 should go here, which is index of 2. And negative 3, 2.5, somewhere here as well. So we hope that it goes to this cluster as well. And this transform method measures the distance from each instance to every centroid. The centroid is the cluster center. So let's look at this one, right? 0, 2. It has a distance of 2.81 to the first cluster, which is to this one, 2.882. And then it's 0.32 to the second cluster, index 1, which is right here. So that point is 0, 2, this point, right? Right here. And then the distance is 0.3. And the first distance being 2.81. And the next distance is to here, it's 2.9. So on and so forth, right? So how do you assign that, right? Essentially, this predicting or this assigning new instance is essentially it trying to do is calculate the distance to all those 5 centroid and assign to the nearest centroid, which turns out to be index 1, which is exactly this cluster. That's how it is working. How about second point? Just give you another example. The minimum distance actually goes to 2.8, still this, because that point is somewhere here. Its nearest centroid is still here. Somewhere all the way here, because it's 3, 2, right? So somewhere, I will say here. So that nearest distance is still belonging to the second cluster, index 1. That's why it's predict to 1, right? Okay, that's how you can leverage kmeans as an application. Now, let's look at the algorithm. How does it work? So what it does is just this graph to help you. What it does is initialize the centroids randomly. In this case, initialize all those 5. And then you try to assign the instances. How do you assign the instances? Based on the distance. For example, this point, no dot is nearest to this one. And this point, no dot is nearest to this one. And this point nearest to this point, right? Centroid. And some of this would belong to this, and the other ones might belong to this centroid. So that comes to the something called the second step, assign the instances, or we call it label the instances. When you label, turns out to be these would be the first iteration of the output, those 5 different clusters, right? Now, based on each one of this, let's calculate the new centroid. So based on this, because of that assignment, not necessarily the centroid would still be this point, right? So you have to do a new calculation. The new calculation shows the centroid becomes this, slightly movement, but this particular cluster, this is let's say orange, right? Kind of orange. That cluster center actually moved quite a bit from here to there, from here to there. So you update the centroid based on the distances. So now you have a new centroid. Next step for new iteration, what you would do is you continue to label the instance to say, okay, all of this are nearest to this. Some of these might be belonging to here. so that the boundary changes, right? So you have got a new label of all the instances. Again, continue with that. Update your centroid. Centroid would move to somewhere and relabel. Continue with this whole process. What it does is update the centroid, label the instances, update the centroid, and label the instances one more time. That shows you that means algorithm in this k-means name, right? That k itself is number of clusters. In this case, you could call it as 5 means algorithm in this example. We're trying to figure out 5 clusters using each cluster's mean to trying to update the centroid, come back with the mean, and continue relabel the instance, continue all the iterations. And at one point, you would have to stop. Question would become, how would you stop? One thing you would think of would be by doing more updating the centroid from here, would your points move much? If it doesn't, then you know you find the solution. In this example, it would stop here because you wouldn't be able to update the centroid. The new centroid, if you continue to update from here, would not move much to the existing centroid. So that's k-means algorithm. Hopefully you got a good understanding of this. So however, it does have the risk of random initialization. So assuming that this is, which is really the case, this is our final solution. If you use different random points, there's a chance that you end up with different solutions. For example, one of the solutions, just you're not lucky, you started with the random initialization of the centroid, and turns out to be these 5 points becomes our new solution of the k-means. So these are not really ideal, right? Those two supposedly to be 2 separate clusters, now it becomes 1 cluster. And another different random initialization, those 5, 1, 2, 3, 4, 5, less than ideal as well. This cluster has been splitted rather than these 2 clusters are not splitted at all. So that's the risk of random initialization. And of course, we have to figure out some solution for getting away from this risk of random initialization. So there are multiple centroid initialization methods that can help you to get away from this random initialization. One of them, number one, based on empirical evidence or other algorithms, is called innate. So you're trying to see, okay, trying to see if you are able to leverage some other information to help you. That's one way. Second way, you can run this k-means multiple runs, and then based on initial of the runs, so that you can make a decision on which one, which random run is the one that you want to pick. That's the second one. The third one is something called k-means plus plus. So let's see how does this work. Right. So what it does is take one centroid C1, which is chosen uniformly at a random from the dataset, and then you take a new centroid Ci, a different point, choosing an instance Xi with certain probability. And this probability is defined as the distance of this xi squared divided by summation of all the other rest of the distance of summation, where dxi is the distance between the instance xi and the closest centroid that was already chosen. This probability distribution ensures that instances farther away from already chosen centroid are much more likely to be selected as centroid. So you choosing an instances with a probability as a new centroid so that you don't want to put two centroid too near. That's the idea. And then you repeat the previous step until all k-centroid have been chosen. This is called k-means plus plus. So if you think about k-means itself, it's only the first step. But now we have 3 steps to make a decision on what are the initialization of the centroid, with the hope that you don't pick the one that's too near to the one you already chosen. That's another way. So let's look at 2 other things. One of them is called accelerated k-means. The second one is called mini-batch k-means. So you can see that we have discussed multiple variations of those 2, accelerated, mini-batch, right? So here I don't really want to continue to elaborate on what is accelerated, what is mini-batch. But in this k-means, you to be specifically for k-means, you try to avoid many unnecessary distance calculations so that you could accelerate your k-means methodology. So if you don't, the default is really you don't need to calculate all the distances just because based on their location, right? If you go back, how does it work? So this is your initial centroid. If you already calculated some of the points to this distance to these points, based on their location or coordinates, you pretty much already know some of those points. You don't really need to calculate. This should, if some of these points are nearer to this centroid, the rest of them should be nearer to this centroid as well. That's the idea. So the default is you don't put anything. It's already accelerated k-means. Or you could put algorithm equal to full so that the algorithm will to calculate all distances. I just don't see why you need to change that, right? So you could use the default. And then mini batch k-means, instead of using the full data set for each iteration, algorithms capable of using mini batches, moving the centroid just slightly at each iteration. So let's look at this one. It is the discussion of the inertia of k-means versus mini-batch. So as we mentioned in the previous slide, it says that we want to find the minimize inertia of the algorithm. In this case, the k-means has a smaller inertia of comparing with mini-batch k-means, which means it's a preferred method from inertia perspective, even though that change is minimal. However, the training time for mini-batch is much less comparing with k-means itself. From this perspective, we definitely want to choose mini-batch, right? Okay. So next question becomes, see, we said k-means. K is the optimal number of clusters. We don't know, right? By looking at the data, if it's easily to be visualized, then you know it would be 5. But the reality is, majority of the time, you don't know how many clusters on your data. So there is a chance that you have bad choices for the number of clusters. So assuming that you use k equal to 3, then what you got is the chart on the left. That's the final clusters. One blue, one gray, one pink, and then that's really not what you want, right? How about k equal to 8, which is on the right? That's not something that you want either. So we have to figure out what would be the proper proper number of clusters. So remember we mentioned initial, and then let's look at k versus initial of this or this for this data set. Then you see that if k equal to 2, it's much larger, and k equal to 3 is smaller, k equal to 4, it's even smaller, 5, etc. With you make your model more complex, you can make your initial smaller, but doesn't mean you want to pick 8 clusters, right? It's the same thing. You don't want to overfit your data. So, and also you want to make sure that it's not, and also you want to make sure the model would be generalizable. Okay, so now you want to pick, in this case, you want to pick the inflection point. In other words, elbow of initial, in this case, would be 4. It's different from 5, right? Now you see that the algorithm, if we purely continue with this direction, we would pick k equal to 4. Let's see what happens if we leverage some other methodologies to come back with a conclusion of 5. Elbow shape and picking the right point. This is also not new. If you think about PCA, right? We are looking at a different elbow, but we're trying to find the dimensions that would be covering enough, and we are not have decreased slope of the continual further improvement in the chart, right? So it's the same thing here. In elbow, we're trying to figure out it doesn't change as much after a certain point. So we call it as inflection point. This inflection point turns out to be 4, number 4 clusters in this example. So that's why we define something else, which is even better to look at than the elbow chart that it can. It's something called Sehut coefficient. It is equal to b minus a divided by max ab, where a is the mean distance to the other instances in the same cluster. A is the mean distance to other instances in the same cluster. In the same cluster, right? Same cluster. So that is the mean intra-cluster distance. We call it intra-cluster distance. One instance, one point, belongs to this cluster, and then what's the mean distance to the other points in this cluster? That's called A. How about B? B is the mean nearest cluster distance. The mean distance to the next closest cluster, defined as the one that minimizes B, excluding the instance's own cluster. So that's B. B is something called intercluster distance. So this point and the nearest cluster is a different cluster, and the mean distance from this point to the nearest clusters or instances, that mean, that average. So we use b minus a divided by max a divided by b to define the relationship between the intracluster and intercluster. Intra meaning within that cluster, inter meaning between clusters. Okay, this Sehut score is the mean of Sehut coefficient over all the instances. So each one of them would come back with one value, and then you average all of them, and it would be Sehut coefficient. Sehut coefficient is between -1 to 1. Close to 1 means the instance is well inside its own cluster and far from other clusters. And close to 0 means that it is close to a cluster boundary and -1 means the instance may have been assigned to the wrong cluster. So let's go back to the example, right? Let's look at this data. Remember we said A is the intra-cluster mean distance. So one of these points, calculate all the distance within this cluster and then get the mean, would be this point, distance to each one of the rest, and then get the mean. That's called A, right? B is the distance between this point to the nearest. Let's call this is nearest. All the points of the other ones, right? And then get a mean. That's that. And then that's called Sehut coefficient. And the Sehut score is something try to aggregate all the Sehut distance for all the instances. Then, so if it turns out to be 1, meaning close to 1, meaning these points are here, and if it's close to 0, would be the ones that's on the boundary, and if it's -1, it's a misclassification, misclustering in this case, misclustering instances. So let's look at this chart. And what we could do is we use Sehut score on the y-axis and the number of keys, and we see that 4 and 5 has higher Sehut score. So that's another way to look at it. We might choose 4 or 5. Now, before we make the conclusion, we use Sehut diagram, which is for different selection of number clusters, 3 or 4 or 5 or 6. And then for each one of them have different, apparently this shows each of the cluster, right? 3 clusters, 4 clusters, and 5 clusters, and 6. Let's see what this diagrams tells us. The height indicates the number of instances to the cluster, the number of instances the cluster actually contains. Let's say the first cluster has a lot of observations, and this cluster doesn't have many, and this cluster has a lot. And width represents the sorted Sehut coefficients of the instance in the cluster. The wider, the better. The wider of this, the better. So just conceptually, you find that some of these are wider than this one, right? So that might be better. Dashed red line indicates the mean Sehut coefficient. Mean Sehut coefficient, we hope that our width of the clusters are on the right side of the red line. So if it's on the left, it's less than ideal. On the right, it might work. On the right, it might work. Some of them on the left, less than ideal. And next thing we want to see is, because we said the height is a number of observations that belongs to this cluster, and then apparently this cluster is much bigger than this one. And then in our case, we want to select the number of clusters that more or less have similar sizes in that cluster, similar number of observations in that cluster. So in this case, we find that k equal to 5 is really the best. It have multiple characteristics. Number 1, it has similar height, meaning similar number of observations in each cluster. Number 2, the width is wide. Number 3, all the maximum of the width lies on the red lines, lines on the right of the red lines, meaning it's beyond the red lines. So from this, we actually select k equal to 5 to get the best number of clusters. Of course, if you choose k equal to 4, I think would be okay as well, just not as best as k equal to 5. So let's think about what would k equal to 4 come back with. Most likely, I would think that these two might be grouped together so that it becomes 1, 2, 3, 4. You could test it on your own as well. So that's something that you should experiment on. Now, let's just quickly review what we studied here. K-means algorithm. It has two things. Algorithm-wise, pick a centroid, update, pick a centroid, let's put it this way. The algorithm is pick a centroid, pick multiple centroids randomly initialized, and label the instances, and then update your centroid. After that, label the instances, and continue with update your centroids. Continue with the whole process, so at one point you would stop when the centroid doesn't move as much. That's number one. Second thing you need to figure out is what is a proper mean? What is a proper k? K equal to 3 or 5 or 8. And then you need to leverage two methodology. One of them is called inertia. Second one is called Sehut diagram. In between, we also discussed kmeans ++ that helps you to get away from random initialization of the centroid. So that's everything that we want to discuss about k-means, and then we can continue with k-means applications in our next lecture. Thank you.